Okay, in this section we're going to talk about constrained optimization, which is basically the same thing as unconstrained optimization. The only difference is now when we're looking at the problem, we're going to have a subject to. All right, so what we're going to do, we have this wonderful equation called the Lagrange multipliers equation, which is this function right here. And it's really kind of simple. We're just going to make a new function based off of our original f of x, or think of it as the original thing you are trying to find the max or min of. And then the g of x equation, the g of xy, is just our constraint. Okay, and the only rule to this is when you're subbing in for this, your constraint has to be equal to 0. So the preparation for this is really simple. You always start off with your constraint equation. We're going to say it's x minus y equals 5, and it doesn't matter which way you solve, you just need to get it equal to 0. So to me, the simplest version seems like it would be x minus y minus 5 equals 0. This thing here, this part here, not including the part 0, the equal 0, that is going to be our g of x comma y function. Okay, now what we're going to do is create our new function. It's f comma x. We have the variables x and y, and this mysterious lambda is about to pop up. Now, what I'm going to fill in for the first part of the equation, what I'm going to fill in for there is my original function we're trying to min or max. That function is this one here. So that's going to be x squared plus, oops, we have a z in this equation too. So let me add in a z here. X, y, z, lambda. Okay. So we're going to have x squared plus y squared plus z squared minus 2. That's my f of x. Now, notice in the equation I have a plus sign. Okay. Then it's lambda times my g of x. That's what I just did here in yellow. So I'm going to fill that in right here. So this is my x minus y minus 5. And there we go. We have set up the Lagrange multiplier equation. Now, how do you do this problem? You do 15.3. You do it the exact same way we've always done any kind of maximization problem. The only thing that makes this kind of worse is we now have a new variable. We have an extra variable, the Lagrange multiplier variable. But just treat it like anything else. Now, for your derivatives, some of you may find it easier to distribute this through. Others may rather just leave it right out here. So I'm going to leave it factored out for a minute and see how we do. So let's see. The derivative with respect to x. So I go through here, and I'm going to say x squared equals 2x. There's no x's in this term. There's no x's in this term. There's no x's in that term. So those are all zeros. Okay, so we can ignore those. Plus lambda times, because it's a constant, so it just sits out here. And I have an x to the first, so that becomes 1 minus 0 minus 0. So I'm just left with 1 lambda, or aka lambda. So my derivative with respect to x is that. My derivative with respect to y, very similar now. That's going to be 2y minus lambda. And again, because the lambda is the constant multiplier, and then the derivative of x would be 0. Now I'm looking at my negative y term right here. So that would be y to the, that would make a negative 1. And then, so the negative 1 times lambda gave me the negative lambda. Okay. And then similarly for the derivative with respect to z, that's going to be 2z. And there are no z's. There are no z's in this function here. So we're done. There's no lambda in that term. And last but not least, I still have to do the derivative with respect to lambda. So the derivative with respect to lambda, there are no lambdas in this first term. It goes away, right? The only thing that has a lambda is over here. It's lambda to the first. The rest of this stuff is a constant. So it just leaves me with x minus y minus 5. And you may be saying, wait a second, Professor Dwork, won't it always just be your constraint equation? Yes, it will. So now we just have a really big system of equations to solve. I have 4 variables. I have an x, a y, a z, and a lambda, and I need to solve them. Now, for those of you who are putting everything together, you may recognize that this is a linear equation, linear equation, linear equation, linear equation, and we're going to take all of these and set them equal to 0. So you could, theoretically, if you have this particular type of scenario, and this happens a lot, you could just put this in a calculator and let it do reduced echelon form for you. Because in chapter 3.1, whatever's. This is where we learned systems of linear equations, reduced echelon form. Great. Now, let me give you my tip though on how to do these by hand, because it will serve you well. Always pick an equation that has a lambda, because we don't want lambda. Lambda, we just made it up. So pick any equation that has a lambda and solve for it. I'm going to solve this equation for lambda. The reason why is because solving for it is going to be pretty. It's just going to end up being lambda equals 2y. So now, in every other equation that I have left, everywhere I have a lambda, I'm going to replace it with 2y. So now this new equation here is going to become 0 equals 2x plus 2y. So that being said, if I had lambdas in other equations, I would sub it in there as well. Now, the idea, I have now essentially finished off this equation. I now have an equation with x and y. I have one equation, whoops, put my pen on the slider. I have one equation with x and y, well, and z. I have another equation with x and y and z, and I have another equation with x and y and z. So let's continue this. Now, using equation number 2 here, you can see I already can solve this, z equals 0. So now I know. I have my answer right here. Anywhere I have a z, it's 0. I'm done with that. So now, using equation 1 and equation 3, these just have x's and y's. So using any technique we've learned in chapter 3, substitution technique, elimination technique, again, reduced echelon form in a matrix, whatever you want. Now the thing you'll notice here is I'm gonna use equation 3 because solving for y is really pretty. Y equals x minus 5. So now everywhere I have a y, I'm going to replace that with x minus 5. So you see, it's a little puzzle. It's just a little puzzle. But it's just substitution. Just keep track of your variables and you'll be fine. All right, so now you'll notice because of that substitution, I have 2x minus or plus 2x minus 10. So what does that give me? 4x minus 10. So I have add the 10, divide by 4. So that's going to give me 5 halves equals x. So now I'm basically done with the problem. I know everywhere I have an x, I can work backwards now. I can work backwards, going back, and replace that with 5 halves. So I have y equals, that's the world's worst 5. There we go, 5 halves minus 5. So that would be what? 5 halves minus 10 halves. So that'd be y equals negative 5 halves. So now I know x is 5 halves, y is negative 5 halves. So I can keep working backwards to figure out my other variable. Oh, good news, I already had that. So my ordered triplet is going to be my x is 5 halves, my y is negative 5 halves, my z was 0, and notice our original function is a 4-dimensional equation. We have 3 input variables, right? We have 3 input variables, x, y, and z. And then I have one output variable, which you can call whatever you want. Typically, we call it w. But in particular, some scenarios, you might call it t for time or whatever. So I now need to take these values and sub them back in to the original equation to get its value. And let me do that off. I'm going to pause the video. And I got 21 halves, or that's the same thing as 21 halves is the same thing as 10.5. So either which way, I now have my answer. The critical value occurs at 5 halves, negative 5 halves, 0, 10.5. Or this problem specifically asked for a minimum. So I am going to have a min of 10.5 at 5 halves, negative 5 halves, 0. So the idea here, you might be saying, all right, what the heck's going on? We have a 4-dimensional equation. How do I graph that? You don't. Okay, that's number one. You can't. But the idea is in business, you may not have, you're not trying to find maximums of a hill. You're trying to find a maximum of a situation that's a profit or a cost or a revenue. So the idea here is, and your company may have 80 variables. Well, good news. You can do this with 80 variables. You just set up your constraint equations with your lambda. And in this class, we're only going to have one constraint. But in future classes, you may have additional. And it's basically the same thing. It's a little tweak, but it's basically the same idea. So you just set up your constraint equation. You set up your optimization equation. And then you do your partials. You set them equal to 0. And then you just have a really, really fun system of equations to solve. and you get your answer. Now, note, we are not going to use the second derivative test. Don't need it, don't care. And you can kind of go back to the theory from chapter 3 about the corner points being maxes and mins. It's basically the same idea, just saying we have an intersections of lines, so therefore this is going to guarantee it's the maximum of that intersection or a minimum of that intersection. So the way you could convince yourself that this 10.5 is a min and not a max, or vice versa, is just substitute in any value into your original equation that satisfies this condition where x minus y has to equal 5. Plug in those values for x and y and z, and you will see that your output will be bigger than 10.5. If you don't care, don't bother. Just trust me, I'm not going to try and trick you and ask you for a minimum and really have it be a maximum. That's not my goal. There's enough going on in these problems that you go through this process, and I am happy. Okay, so that's it. So the big idea, what is new about Lagrange multipliers? You set up your equation, and then you do 15.3, right? You just do your derivatives, set them equal to 0, and solve. All right, we'll see you in the next video, the practice.